So my name is Jason Gooley. As said earlier, I wanted to thank everybody for coming out today. I appreciate it. I want to introduce our first speaker today, and his name is Dr. Aditya Akella. He's actually will be presenting the designing and experimenting with data center network architectures. So Aditya is a associate professor of computer science at the University of Wisconsin-Madison. And if you guys have heard of CloudLab, he's going to actually come up here today and talk to that. That is basically it's a research-based cloud computing project. And he'll be coming up right now and speaking on that, and I want to thank everybody. So thank you so much.
Okay. Hello, everyone, and thanks for having me here. This talk actually has two parts. The second part of the talk will actually cover CloudLab. But in the first part of the talk, I want to talk about some work we have been doing on data center network designs and putting a variety of proposals that have been out there in perspective. And in the second part of the talk, I'll talk about infrastructure we've been building that allows researchers to experiment with various new ideas in data center networks, storage and virtualization as it pertains to data center infrastructure, and various other aspects of cloud computing. Can people hear me, or should I wear the microphone? I'm not wearing the microphone. You can hear me. Okay, great. Okay, so I don't need to say this to this crowd, but with many, if not most, important services moving to the cloud, data center build out is happening at a very rapid pace. The projected amount of money that we are expected to spend on building data centers is likely to be in the tens of billions of dollars in the next few years. And this has been the case for several years now, starting around maybe early 2000s. This has really picked up pace. And so all this interest in designing data center networks has spurred sort of a little cottage industry in the networking research community, with groups of researchers busily trying to figure out what the right data center network architecture ought to look like. So there have been a variety of proposals for coming up with the right way of interconnecting racks inside a data center, systems or ideas named like fat tree that appeared in SIGCOMM about 7 years ago, something called VL2, D-cell, B-cube, jellyfish. And this is a small list. There's been a variety of different proposals of this particular kind. So here's an example of the factory data center interconnect topology. So it is composed of commodity Ethernet switches. Each switch has a constant fan out of 4, and it has 1 gig links going out of it. And so the choice of the switch and its fan out kind of determines the size and the overall provisioning of the data center interconnect. The interesting aspect of this topology is that it has an oversubscription ratio of 1, meaning that it can support very high bandwidth transfers across the interconnect between pairs of servers in these racks. This is a more recent one. It's called VL2. This came out of Microsoft. And this is pretty close to what is deployed in some of the biggest data centers, at least at Microsoft today. This is also referred to as a folded clause topology. Many of you may have heard of this. The difference from what we saw earlier in terms of fat tree is that the links are not all of the same uniform 1 gig capacity. Servers have 1 gig links, but the rest of the interconnect uses 10 gig links. There's again the spine layer, the ag layer, and so on. This may be more familiar to what you have. And again, this has a very good oversubscription ratio of 1. In addition to fat tree and VL2, there have been things like D-cell, which is actually a click of clicks, if you will. There's something called B-cube, which is basically a mesh of stars. It kind of looks like the logo on the CHI-NOG t-shirt. And jellyfish, which is essentially a random graph that interconnects servers. And so there have been a variety of different proposals for these interconnects. So as a data center architect, you may be wondering which of these do you pick, and how exactly do you compare these different proposals when it comes to you building your data center network. And there are a variety of different attributes to consider for each of these networks, like what kind of bisection bandwidth they provide, how long paths are, what kind of switches do you need to use, what kind of fault tolerance it offers, and what the overall cost of building this data center infrastructure is, and so on. And all of the things that I showed you, VL2 and fat tree, they are good in some of these respects. Some of them are good in some of these respects and bad in other respects, relatively speaking, with respect to other ideas. So what my group has been doing in collaboration with researchers at Duke University and Microsoft Research is trying to bring together a more principled approach, coming up with more scientific rules of thumb, if you will, for designing data center networks. In particular, we have been pushing this notion of a universal approach to data center network design. And essentially, a universal data center network is one that is competitive, no matter what application you want to run in the data center, with any other network that can be built at the same cost. If you're able to come up with a universal data center network, the advantage would be that you wouldn't have to worry so much about how your choice of the network compares against what people call the state of the art in terms of various respects, because it's always going to be competitive no matter what application you are wanting to run inside your data center. So can we come up with a universal data center network architecture of this particular kind? So our inspiration for this universal approach comes from this notion from the parallel interconnects world, where people have done a lot of work in the parallel computing world, connecting up processors and building networks on chips, where many years ago, many decades ago, the researchers had a similar conundrum as we face today, with a bunch of different proposals for interconnection networks, like Benet networks and class topologies and fat trees and all of these different things, and no clear ideas as to what is the right choice for the interconnection network. And so back in 1985, Charles Lyserson, a professor at MIT, came up with this interesting notion of area universality, and showed that certain networks can be area universal. In particular, he showed that a particular kind of what are called fat tree networks are area universal, in the sense that a fat tree network can emulate any other network that can be built in the same area with a constant slowdown in the performance of applications. Okay? So this slowdown order polynomial in the logarithm of n may seem daunting, but this is the worst case slowdown that any application can face, meaning that this fat tree network, or particular kind of fat tree network, can emulate any network that you can build in the same area. This is what area universality is all about. And this bound was later improved to order log n, and the area was later replaced by volume for 3D interconnects in the parallel interconnection world. So let's look a little bit deeper into what these fat trees are. And these are not fat trees as we saw in the earlier picture a couple of slides ago. These are very different. And let's look at what area universality means and why these fat trees are area universal. So here is what a fat tree looks like. At a very macroscopic level, it is exactly like a tree. At the bottom are all the processors that you want to interconnect. And there are a bunch of internal nodes in your fat tree. And these nodes are interconnected by bidirectional channels. And the designer of a fat tree, this is for a network on a chip, can choose the fan out of this core structure. In this particular case, the fan out is 4 throughout the tree. If you peel and go one level deeper, there's a fine structure to the fat tree, where each of the internal nodes in the core structure is replaced by a bunch of switches. So the root is replaced by these 4 switches, and the children are replaced by these 2 switches. And the channels are replaced by links between switches in one layer and switches in another layer. Okay? And there are various ways in which you can interconnect the nodes, the actual switches in a fat tree, but this particular kind of interconnection is also called a butterfly fat tree. And the key property is that there are no links between switches in the same layer, and each parent node has a link to exactly one child in the core structure of the fat tree. Okay, so this is called a butterfly fat tree. And what Charles Lyserson showed is that this particular fat tree can be configured to be area universal. So let me give you some insights as to why this particular network can become area universal, and that will lead me to how you can build universal data center network designs. So the important point to notice about fat trees is that you can keep the core structure the same, but you can twiddle with the capacities or the bandwidths you allocate to the channels in connecting the different layers to achieve various properties. So one such twiddling of capacities results in a fat tree topology that is area universal. So here is how you would go about building that kind of a factory network. Let's say you want to realize a network that has a core structure with a degree of 4, as I showed to you earlier. So the way you would do it is you would start with a chip, let's say laid out on this square area. You would divide it into 4 quadrants. And this is what it would look like at the root of the core structure. And then the capacities you would allocate for each channel going out of the root equals the maximum number of wires that could be cut by each of these quadrants. Okay? So you're trying to maximally provision the cables cutting across these different quadrants. So suppose you have n processors that you want to lay on this chip. You can think of each side as being square root n. So the maximum number of wires, assuming unit width wires, crossing these boundaries is going to be square root n. So the capacity of each channel, the aggregate capacity of each channel is square root n. And there are 4 such channels, so you end up with a total capacity of 4 square root n going out of the root of your core structure. And you repeat this process recursively in each quadrant. So again, you go down into this quadrant, divide it into 4 quadrants, do the same thing. And what you realize is once you go one level down, the total capacity is 8 square root n going out from that layer to the children. And so the capacity actually doubles every layer. So if you actually, this is the logical way of thinking about it, but if you physically lay it out, I don't know how many of you can see this picture of the physical chip layout of a factory. It kind of looks like this. So these squares are all processors. There are 64 processors that you're trying to connect here. These ovals are switches. These are the internal switches in the core, in the fine structure. And these lines are cables that are connecting these processors to the switches and so on. So like I said earlier, the aggregate capacity as you go down from the core structure to the finer structures doubles. But what you see from this picture is that the length of the cables halves as you go from the root to its children and so on, right? Because the cables become shorter and shorter as you go lower and lower in the hierarchy. And what that means is the capacity is doubling, the length is halving. So if you imagine unit width cables, the total amount of area you're spending in laying out wires at any layer of the core structure stays the same, right? Because the capacity is doubling, but the lengths are halving as you go down, right? And that's exactly the idea of an area universal topology. In the case of VLSI networks, the way you would build it is you would build a hierarchical network, but you would allocate the same amount of chip area for the wires to interconnect any one layer in your hierarchical network. Now the reason the topology ends up being area universal is that suppose you want to emulate some network n using this factory topology, you would take that network n and you would logically cut it into 4 quadrants. And you would basically then ask, okay, do I have the capacity to go across quadrants, and can my factory provide that capacity? Recall that we maximally provisioned the capacity, crossing any edges. We gave the maximum amount of bandwidth possible, so we have as much bandwidth as needed for any inter-quadrant traffic in that network n. And the way this factory would emulate that network n is whenever the network n wanted to send a message on a particular link, the factory would basically, send a message from one leaf to another leaf. So if the message were to go across quadrants, then the factory would pick a leaf in one quadrant and send the message to another quadrant and so on. And because this is a hierarchical topology, each message traverses a path that is only order log n longer than what it would take in the native network n, right? So this is how you can emulate any given network, but each path ends up being order log n longer than what you would see in the original network. Okay? This is the notion of area universality and how factory supports it. So this is what brings us to our notion of a universal approach to data center network. Similar to, motivated by what people came up with the idea of how to do this in the interconnection network world, what we would like to propose is to spend the same amount of money to the infrastructure you provision in each layer to connect the gear that you have deployed in a particular layer or level of your data center network architecture. And of course, there's no notion of area in data center networks, so the equivalent quantifiable thing here is dollars. So the levels here, you can think of the bottom level as basically the servers in your rack and the interconnection between those servers and top of rack switches looked across all racks. At the next level, you have all racks in a row. And at the very top level, you have interconnections across rows. So you want to spend the same total amount of money in these 3 levels. So essentially what this boils down to is this following rule of thumb. Let's say you're given a set of servers that you want to hook up in a hierarchical data center network. You spend the best possible technology you have at hand to connect up the servers at the lowest level with each other and with their top of the rack switches. And that corresponds to some dollar amount. And then you would want to spend the same amount of dollar amount in hooking up those racks in a row and hooking up across rows. That gives you a cost universal data center network, a network that can emulate any other network at exactly the same cost. Does that make sense? Okay, so there are a few caveats to this argument. The first is that we assumed that the performance that you derive is proportional to cost. And when you provision 1/3 the expense of a network, you get 1/3 lower cost and so on. We also assumed that it is physically possible to spend the same amount at each layer. Depending on the technology, this may not quite be possible. And we also assumed that the key bottleneck for performance is bandwidth oriented and not really because of latency and things of that kind. So this is for a specific class of networks that this argument would hold. So after coming up with this notion, and the paper we wrote corresponding to this provides proofs as to why this is cost universal, and we do a bunch of simulations that show that in practice, depending on no matter what applications you run, you end up getting reasonable performance on these cost universal networks. Another interesting thing we did was we basically looked at all the networks that Microsoft had designed for their data center networks over the past 10 years or so, going from something like 2005 all the way up to 2014. And we looked at whether the design patterns that the designers in those networks were following our notion of cost universality and how far away they were getting from the notion of cost universality. So 5 years ago, maybe in about 2009 and 2010, the networks that were built were very tree-like. So a lot of money was spent at the very lowest layer, hooking up to top of racks. A lot less aggregate money was spent in the next layer and far less money in the highest layer. And these networks are not cost universal and they're not competitive. But more recent networks, sort of like the VL2 kind of design that I showed you, are approaching the cost universal design, where the amount of cost allocated to each layer is essentially roughly equivalent. This also points to something I hinted on earlier, which is essentially about not maybe having the technology around to provide the same amount of dollars at each level of your hierarchy. So what this basically shows you is that if you didn't have the technology to push this in this particular way, you try to get as close to the equal split ratio as possible. So for good or bad, mostly for good, most existing networks, it seems like, are already being built in sort of a cost universal fashion. So that actually brings me to the second part of my talk. So the first part was basically about reasoning about what proposals there are for data center network architectures out there and trying to put them together in one framework and coming up with this notion of cost universal designs. And there's been a bunch of other interesting work on designing data center network architectures that suit various particular kinds of requirements. And people in the systems and networking community have been doing a bunch of other interesting work in the data center context in storage and virtualization and so on. What was missing for the largest part is a large-scale test bed where people can try out these ideas. And that brings me to CloudLab. This is an infrastructure we have built in collaboration with researchers at University of Utah and Clemson, and BBN, UMass, and the US Ignite Corporation. So let me tell you a little bit more about what CloudLab is and what kind of needs it addresses and so on. So again, in the first part of the talk, I described to you this data center network architecture. But given an architecture for servers and the interconnect, there is still a lot more that you would want to do in terms of optimizing the software, maybe, for example, to cut out any superfluous latency. And given the software and hardware infrastructure, you may want to figure out how best to design applications and run them so as to leverage the capabilities that the hardware and software provide in the most ideal fashion. And these kind of issues arise in a variety of different areas, including storage, networking, virtualization, and so on. So what CloudLab is a framework that allows researchers to explore these questions. It is built basically as a flexible and scalable scientific infrastructure Our goal is to enable researchers to explore what we think are fundamental questions in the design of data centers and data center applications. And the key thing we want to enable is reproducibility of research that people do in this particular context. If I come up with a design of a data center network architecture and I evaluate it in CloudLab, someone else wanting to follow up and improve it should be able to reproduce what I did and improve on that. So the CloudLab vision is the following. The first thing I want to mention is that CloudLab is not a cloud. It is a meta cloud in the sense that as a researcher, you get to build your own cloud on the hardware resources that we provide to you. We are not tied down to any particular cloud software. We are agnostic to cloud software. You can run existing software stacks, for example, OpenStack or Hadoop or whatever else they might be. Or you may build your own stacks from the ground up, deploy your own kernels, make custom modifications, build your own schedulers for cloud computing applications, what have you. And the key thing though is that no matter what you build, CloudLab gives you control and visibility all the way down to the bare metal. And from researchers' point of view, we want to make it very easy to use. Today you can spin up a VM incredibly easily in a place like EC2. We want to make it as easy to spin up a cloud or a data center instance in CloudLab. So CloudLab is composed of these sets of resources that are spread throughout the United States. There are a bunch of clusters that I will describe shortly, deployed at Utah, Wisconsin, and Clemson, and a bunch of resources, basically racks of compute that are sprinkled across the United States as part of infrastructure called Genie. And all of these are connected through a variety of federally funded systems out there, such as Internet 2. And essentially what CloudLab, if you have an account at CloudLab, what users get to do is they can run experiments within slices that can span multiple subsets of this infrastructure. So there could be a slice that is running a particular kind of a virtualization experiment running on the Utah and Wisconsin, across the Utah and Wisconsin clusters. There can be a separate slice running allocation and scheduling for cyber physical systems running across multiple other slices, multiple other infrastructure components, and so on. So a quick glimpse into the hardware that we have deployed so far in CloudLab. Like I said, there are these three big clusters around which CloudLab's design and operation are centered. Each of these clusters is built in collaboration with a particular vendor. So for example, the Wisconsin cluster is built with Cisco, the Clemson cluster is built in collaboration with Dell, and the Utah cluster is built in collaboration with HP. And each of these clusters is provisioned slightly differently from the others so as to provide more unique capabilities in one dimension. So for example, the Wisconsin cluster is very storage and networking heavy, enabling interesting storage related and memory related experiments. The Utah cluster is power efficient, enabling research into power efficient data center and cloud application designs possibly. And the Clemson cluster is very heavily memory provisioned so as to do interesting research in terms of storage hierarchies or memory-oriented object stores. On the whole, you have, as a researcher, you have access to about 15,000 compute cores deployed across these three setups with 100 gigabit connectivity through Internet 2, and again, software-defined networking enabled on the top of the rack switches that we have deployed in each of these clusters. So let me give you a bit more detail into exactly what this looks like. Here's what the Wisconsin cluster looks like. It's sort of like what I showed you for the VL2 architecture. It's a folded clause topology, if you will. At the bottom, we have our 12 racks worth of compute. Each rack will eventually have 40 servers, and each of these racks has about 20 servers, and each server has dual 10 gig NIC connected up to a Cisco Nexus 31000 series switch. So these form the top of the rack switches. These switches are connected to a spine layer, again composed of Nexus 3000 series switches via 40 gig links. So this essentially provides full bisection bandwidth between all sets of servers in this deployment. These are then connected through a bunch of 40 gig links to a core switch. Again, a Nexus 3000 series switch, which is then connected to the rest of the campus and to other portions of CloudLab through the 10 gig links. So this is essentially a data center topology, and when researchers sign up for experiments, they can get slices of these infrastructures. They can check out entire racks, or they can check out VMs on individual machines, or they can check out machines. They can program the switches and go all the way through the infrastructure to other parts of CloudLab. So the compute kind of looks like this. We have a bunch of Cisco M4 chassis servers. So far we have about 100 servers deployed, largely limited by NSF's rounds of funding. The first set of these servers are small form factor servers, and there are a small number of large form factor servers. All of them have lots of cores of CPU and lots of RAM, and each of them has one SSD. The differences among these two servers, the small and the large form factor, is that the large form factor servers have a bunch of hard drives. Each of them has about 12 3 terabyte hard drives that were donated by Seagate that could be used towards interesting storage and memory-based research. Over the next year, we plan to add 140 additional servers to this cluster, and then eventual plan is to grow the cluster as well by deploying additional racks. And our plan is also to spend a bit of money to deploy additional accelerators to our cluster, things like FPGAs and GPUs, to enable researchers to offload some of their computation to these accelerators in this kind of a setup. The networking, like I said earlier, is Cisco-based gear. All of this supports OpenFlow 1.0 at this particular point. We're working with Cisco on trying to get OpenFlow 1.3 supported on them. The other clusters at Clemson and Utah already have OpenFlow 1.3 support. All of these switches can allow you to spin multiple virtual routers on each of them, and each researcher can have their own programmable virtual OpenFlow switch or sets of switches in their deployment. And they can do a variety of different things like monitoring fine-grained Q lengths and fine-grained control plane actions and so on. All of this capability has been exported programmatically to the researchers. So a quick view into what kinds of experiments people can do and what kind of technologies people can develop on top of this. So for example, because we have a full bisection bandwidth network and the NICs with capability for offload, we can use it to study a variety of different ideas for data center load balancing and interesting new ideas for offloading some of this functionality to data center NICs. So for example, my group developed this system called Presto, which provides zero loss load balanced data center network abstraction purely in software by offloading the load balancing functionality to the NIC and using TSO and GRO functionality on the NICs. And we experimented with that idea using CloudLab. Others have developed things like Conga, and there are data center transport architectures like DC-TCP that could be experimented with on CloudLab. We have also developed a system for network functions virtualization. This is an orchestration control plane, if you will, for NFV called OpenNF, which allows a system to control a collection of network functions, chain them together, elastically scale them up or down, or take them down and whatever. And we've used the capabilities provided by CloudLab as a way of designing many of these network functions and for designing the control plane for these network functions. Because these systems also have lots of memory in them, you can experiment with a variety of in-memory big data frameworks, things like Spark and Shark. My group developed a system called Graphene, which is basically a scheduler for many of these in-memory data center cloud computing frameworks that, again, we have experimented with on CloudLab. And you could do a variety of cloud scale resource management systems. Think of these as schedulers that go into Yarn or Tez or other such cloud computing frameworks. We've developed something called Tetris, another scheduler that does multidimensional bin packing, and things like Mesos can be natively run on CloudLab as well. And finally, you can experiment with different interesting new models for cloud storage, such as tiered storage, where you have memory, SSD, and hard drives, synergistically working towards the kind of storage abstractions that you can build inside a cloud. And you can also explore new storage architectures such as RAM Cloud, where you use essentially the large amounts of memory that the servers provide to essentially build object stores. So these are the kinds of research that we can use. Already it's being used for some subsets of these projects, and a variety of interesting projects are also happening as we speak. So this is built on what is called MuLab. MuLab is an experimental infrastructure that came out of Utah several years ago. And essentially what MuLab gives you is a nice graphical user interface for specifying the topology, Once you specify the topology, MuLab goes out, boots up the machines in the necessary software if you have provided that, hooks them up to switches, and then it gets out of the way. The infrastructure is yours. You can program it, you can muck with it any way you want. Eventually we want it back because we want to give it to someone else. And that is up to the experimental software to swap in or out experiments. MuLab's experimental software is built as a scientific instrument. It provides isolation across different resources. So because everyone has to apply for a project, we have a pretty clear idea as to which set of resources to give to each project to keep them isolated from each other. And once you've created a project and you've created interesting software within your data center architecture, you can make a profile out of it. Think of it as creating a virtual machine image. And you can provide that image for other researchers to use. So they can boot up your experimental image and build on top of that. And we have the necessary paraphernalia to support that. So sign up today, it's available, cloudlab.us. You go to the login page, you see the sign up page, you can sign up for an account, and then you can start to run your projects on CloudLab today. And you can also see a list of current ongoing projects that are happening at CloudLab. That's the end of my talk. I covered two very different things, data center network theory, if you will, and experimental infrastructure for supporting cloud and data center research, and I'm happy to take any questions.
So you have about 5-10 minutes to take some questions.
Yeah, sure. Yeah.
How much does it cost to sign up for CloudLab?
It's free. It is mainly targeted at for research purposes and for academics, and of course people in research positions at various places. So it is federally funded. It is absolutely free. If you are in the industry, you'd have to email us about what it is an acceptable use of this particular infrastructure. But it is absolutely free. Yeah.
Are there any open source projects that have been tested at CloudLab that are not happy yet?
Not yet. Not yet. So CloudLab actually started running in February of this year. That's about like 3 months ago. So the number of projects is still a handful. A lot of the projects have some academic involvement in them. So the project I showed you for data center load balancing is in collaboration with IBM, but it has us involved in it as well. So it's an open source academic involved project, if you will. But then we haven't seen any non-academic projects as yet, but we've seen interest from people, and we are kind of figuring out with NSF as to what is an acceptable use policy outside of academics. Yeah.
Interesting victories with things published based on research at CloudLab?
Yeah, absolutely. So Presto, the data center load balancing, is going to appear at SIGCOMM this year. The scale that CloudLab provides, and we required TSO and GRO support and the ability to muck with those things at fairly low level at scale. And we did not have access to test beds at our institution or at IBM even to pull it off. So at CloudLab, we were able to spawn a 100-node test bed that enabled us to do this experiment. So, and what the reviewers of this paper really appreciated was the experimental part of this work and the fact that this may be available for other researchers to build on top of. So, so that's one example. Others in my group at Wisconsin have developed an I/O scheduling framework, a split-level I/O scheduling, that again leveraged CloudLab's support for storage and memory to be able to do scheduling in a cross-layer fashion, going from the buffer cache all the way down to the disk. That is as yet unpublished, but they have used it towards building some of their experimental work. We've gotten a lot of other interest from people asking for things like RDMA support, hardware support for virtualization, and these are things that we continue to enable as we go forward, and we will see, hopefully, that more and more researchers will want to use it toward their experimentation. Other questions?